Good morning, everyone. So we are currently a good number of people attending the opening session. I would like to welcome everybody to DTIP 2021. I'm really happy to share this conference for the last year. We will discuss that later. And I will start by giving you some information on the conference, on the symposium. And then we will have the first day of our conference with a set of very interesting papers. So first of all, I would like to thank all my colleagues from the organizing committee. So the Vice General Chair, Emile Martensik, the publication co-chairs, Frédéric Mailly and Corinne Dejoux, the conference co-chairs that works a lot to build this very interesting program. So Peter Schneider and Jérôme Julliard for the computer-aided design and test conference, and Stewart Smith and Abdelkrim Talbi from University of Lille for the microfabrication, integration and packaging conference. I would like also to give credits to my colleagues from under the communication, the website, and the paper submission website also. A few data regarding the symposium. Honestly, we discuss a lot of having a symposium this year or not. We decided to organize the symposium, even if the sanitary situation was not good. And we decided to organize it in a distant way using the Zoom platform. I hope everything will work perfectly or correctly. Of course, the number of submissions for this year event was far away from the classical numbers. Normally, we receive between 80 and 100 submissions. This year, only 40. Last year, we already have a reduction, and this year, a new one. So the reduction is more or less the same for both conferences, for both aspects. And of course, the number of authors has been lower, the number of reviews, the number of reviewers, everything was lower. And we decided to keep an acceptance ratio of 50% for oral presentation. So this is the reason why there is 20 oral presentation. But most of the paper was at good level. Some of them only having some preliminary ideas or things like that. And we decided to give the microphone also to 14 contributors as a short talk. So it will be similar to the oral presentation, but shorter. So 7 minutes and not 15 like for the standard oral presentation. In both cases, there will be a small question and answer session at the end of 5 minutes. The submitted papers come from 12 different countries. Once again, this is far away from the classical figures, because normally we have 20, 21, 22 different countries with papers. Classically, France and Germany are on the top, and of course Asia with India, Japan, China, and so on. and some other countries to finish the set. Now, before starting the conference for real, I would like to thank my colleagues from the technical program committee. Of course, the conference co-chairs and all the people that accept and to review the papers and give the marks and give comments to authors. And you have here a list that is not maybe readable using Zoom, but you can have the complete list on the website of the conference. Very quickly, an overview of the conference program. So the conference program is very simple. Each day during 3 days, we will have a live session starting at 8:30 a.m. So Paris time. Oral presentation and short talks, so 15 minutes or 7 minutes. Some people prefer to have a pre-recorded video, so we'll have some broadcasted videos. And for others, we will try to have a live presentation, like mine, actually. And what we try to set up is to have dedicated rooms for discussion with presenters and even other attendees after each session or couple of sessions. So you will see that in the detailed program. After each set of presentation, we will have private discussion room or discussion rooms that will be open. So, for example, 7 in the first case, in the first session. And each attendee will be free to choose this room to meet the authors of the papers. So each presenter will be in a specific room. We also have, for those of you that need maybe more time to figure out or to see again the presentation, we will have a replay of the session on DTIP YouTube channel. The link is on the program page. And the session will be available about 2 or 3 hours after the end of the morning session. You all have access to the proceedings, so the papers, the camera-ready papers that are already available and will be published after the conference in IEEE Explore. Some papers are too late, and in that case, we put the paper of the submission. And if you have additional questions, don't hesitate to contact me by the chat or to send emails to DTIP. A more detailed program. So we will start just after this short introduction with Nadia Kim. That is, hello Nadia. That will present his company, next one, and their products. So Nadia is one of our main sponsors. So thank you, because thanks to you, we can offer free registration to many students all over the world. And I don't know the exact figure at that time, but I guess that we will have more than 100 registered people at the end of the symposium, and a lot of PhD and master students. So this is really interesting for us and for them to see what is a conference. And thanks to you, it was possible. After that, we will have the first technical session that will be chaired by Jérôme Julliard on system level design and signal processing. And then we will have the first coffee break corner. So similarly to what happened in real life symposium, we will have 7 breakout rooms that will open after the end of session 1. All attendees will be invited to join a room. So for example, Nadia will join breakout room number 1 as the speaker allocated to this room. And everyone that want to discuss about Nextron company, job opportunities, who knows, or products and so on, will have to go in the breakout room number 1 to have not a private, because you will not be only 2, but a discussion on the group for discussing about Nextron in general. And there will be 6 other rooms that will be allocated for the speakers of session 1. Then I will go faster to present the rest of the program because it will be similar. So after the coffee break corners, I will close at 11 the rooms. So you will have 60 seconds to finish your discussion, exchange your mail or phone number, I don't know. And then you will be back to the main room at 11 past 1, if you are using the 60 seconds, where will be set the session 2. And we will have a coffee break corner to finish the morning. Maybe this last coffee break corner, I will let the room open because there will not, we will not have a new session after. Tomorrow it will be more or less the same, except we will have 2 sessions, 1 coffee break corner, 1 session, 1 coffee break corner. And for the last day, similarly, 1 session, 1 coffee break corner, 1 session. The closing session that will be delivered by my friend and Vice General Chair, Emil Martensik, for the closing session. And the coffee break corners for the session, the 7th session. And also, Emil will be available to discuss with you about maybe next year event. Last but not least, I would like to thank the steering committee, all the members of the steering committee that are steering the conference for years now. And finally, I want to give my big thanks to all the sponsors, my lab, my university, the CNRS, C2N from University Paris-Saclay, IEEE for the Electronics Packaging Society and IEEE, and of course, Nextron, our main industrial sponsor this year. And this is the 2nd year, I guess, you are sponsoring DTIP. So thanks a lot, Nadia, and thanks a lot to your company. So we are nearly on time, 8:48, not 8:45. To listen for Nadia. Nadia, you will have about 10 minutes for your presentation and 5 minutes for questions. And then everyone that wants to discuss more deeply with you will join you in your breakout corner. So Nadia, you can share your screen. If you have some slides, turn on your microphone and we are listening to you.
Okay. Could you see my screen?
Perfectly.
Good morning, everyone. I'm Nadia Kim of Nextron headquarters in Korea. First of all, it's an honor to me today to have a presentation all of you. And I also thank Professor Pascal for giving me an opportunity to introduce our product at DTIP conference. What I'm going to talk about today is microprobe station, our main product. I hope you can find the answer of why microprobe systems. I will begin by briefly looking through the contents of my presentation. Firstly, the overall explanation of microprobe system. What is microprobe system? And next, the distinguishable features and advantages from usual probe stations. Secondly, I will move to the specific model and options of microprobe system. For the last, I will look at the application and the customers of our product. Microprobe system is measured and analyzed to electrical and optical properties of materials under various environmental conditions. It consists of probes for electrical contact. This is 4 probe chamber, you can see. The number of probes could be adjustable if necessary. Thermal stage is at the center of the chamber, and it has 2 gas ports and 4 electrical feed-through. As you can see, its compact size, it's about palm size. Actual dimension is 14 by 7 centimeters. Thanks for its compact size, it's easy to use it with other instruments such as microscope, Raman spectroscopy, and vibrometry. The inner volume is less than 100 cc, so you can make it vacuum quickly, and you don't need large amount of gas when you control the gas atmosphere chamber inside. Regarding the test condition, you can control temperature, vacuum, humidity, and gas flow also. Unique probing method is the most interesting point of microprobe system. You can move the probe in any direction freely. It has special spring structure, so it holds the sample on the stage while making the electrical contact at the same time. Let me show you a short video clip showing how the probe works. First, place your sample on the stage, and you can move the probe with your hand like this by using tweezers. It keeps stable contact even the sample is moving. Turn on the next page. There are several kinds of probe tips we have. First, tungsten-based probe in 50 micron or 100 micron size. Depending on the operating temperature, rhodium coating will be applied to avoid oxidation issues. We also have relatively bigger probe tips. Inconel alloy tip in 300 micro, rhodium wire tip in 250 microns. The bigger the probe tip is, it is more durable and has a stronger ability to fix the sample. Moving on to the temperature range. The most popular one is the middle temperature range, -40 to 200 degrees. For high temperature one, it can go up to 1,000 degrees Celsius. And for low temperature, liquid nitrogen model can go down to 80 kelvins. These are options for fine adjustment. digital microscope, and external micropositioner. If the electrode is too tiny to probe with bare eye and hands, these can help you to adjust it precisely and accurately. You can see the chamber with 6 probes and 8 probes. As I mentioned earlier, the number of probes could be selectable. Our standard is 4, 6, or 8 channels, but it can be customized on your request. We are developing 13 probe version recently, and it would be completed middle of September. The chamber in the right is the one with a multi-pin terminal block connector instead of the probe. If you don't use a probe and using wire bonding or soldering, this can be a good solution. It makes it easy and convenient to make electrical contact through wire without worry about short. And this is microprobe system for LCC chip. LCC socket is already equipped in the chamber. You just need to change the chip carrier only. 28 pins and 48 pins chip are available, and airside cable to connect the chamber to the electrometer like Kisley will be provided together. And this one is dual Peltier stage for thermoelectric devices. You can make temperature difference on the same sample during the measurement. And this is RF probe system. RF probe on the manipulator equipped inside the chamber. The maximum frequency is about 40 gigahertz. Other ports and connector also could be customized if necessary. And this is XLD probe system. It's designed to use in XLD. This system can be used for electric field-induced phase transition in ferroelectric materials research, ion-based battery analysis. And this is a subsidiary option for humidity control. A humidity sensor will be installed in the chamber, and the humidity will be controlled by getting a real value of feedback from the humidity sensor. And this is similar option but for gas control. Up to 97 gases are available, and humidity control and gas control will be done through our dedicated software. And this cute stage is AFM cooling and heating stage. It can be used in AFM. And this is one example of the application compatible with microprobe system. The equipment in the picture is vibrometry of Polytech. As shown in the graph on the right side, you can get more sharp data when controlling the test condition using our chambers. Raman and photocurrent mapping is the most common application of microprobe system. Many of our customers study in this field. And gas sensor is perfect for our chamber. And you can see more applications here: photovoltaic, IV measurement. And these are our global customers. Our customers are very satisfied with our chamber, and it leads them to repurchase our chamber. Second chamber, third chamber. Okay, we are coming to the end of the presentation. Would anyone like to ask questions?
Thank you, Nadia. Effectively, we have 1 or 2 minutes for question, if some. Otherwise, people will join you in breakout room number 1 at the next session, the breakout session. Is any question in the room? I have the opportunity of seeing your product. It was in Paris 2 years ago, I guess. And it's very nice engineering, Nadia. Very nice products. Okay.
Thank you.
If we don't have any question, no question on the chat, maybe you will have some visits in the breakout room later. So thank you very much, Nadia, for your presentation and your nice movie. And Jérôme, do you have a question?
No,
I've seen you are a user of these equipment. No.
Actually, it's not me. It's someone else in Central Supélec.
Okay. So Central Supélec is one of your customers. Okay, so thank you, Nadia. See you later in the breakout room number 1. And
Thank you for your having time. Yeah.
Okay, I hope so. Now I will give the microphone to Jérôme that will chair session number 1 on system level design and signal processing. So Jérôme, it's up to you.
Okay, thank you, Pascal, for the introduction. So welcome everyone to this session on system level design and signal processing. We have 6 talks today, 3 long talks and 3 short talks. And the first speaker will be Andreas Voigt from TU Dresden, who received the diploma degree in physics and the doctor engineer degree in electrical engineering from TU Dresden in 2004 and 2010, and a PhD was on laser techniques for fluid flow measurements. Now, he's a postdoc researcher at the Chair of Microsystems Technology at TU Dresden, and his current research interests include modeling of microfluidic components, modeling and simulation of microfluidic chips, and the creation of tools for the computer-aided design of microfluidic systems. Now you have 15 minutes to present your talk, your paper, Andreas.
Thank you very much for the introduction. I'm going to share my screen now. Can you see the screen now?
Yes.
Okay. So the topic of my talk is a method for the computer-aided design and simulation of hydrogel-based microfluidic chips. My name is Andreas Voigt. I'm from the Chair of Microsystems at Technische Universität Dresden in Germany. I'm going to first explain what I mean by hydrogel-based microfluidics. And then secondly, I will talk about the computer-aided design method. What is microfluidics? Microfluidics deals with the miniaturization of liquid transport, and the final goal is always to construct a laboratory that is integrated on a chip. And this chip, as you can see on the right-hand picture, has small chambers and channels, and the liquids on the chip contains chemicals or cells. And the goal is to control these liquids in such a way that we achieve mixing of liquids, or that we can separate chemicals or cells from the liquid in order to control biochemical or biological processes. Now I'm going to explain what is hydrogel-based flow control. That's a method developed in our group. And the basic component is the chemo microfluidic transistor. This microfluidic transistor is based on stimuli responsive hydrogels. On the left picture, you can see such a hydrogel, and the key idea is that the hydrogel size depends on the chemical concentration in the liquid. So if the chemical concentration is low in the liquid, the hydrogel will be swollen. And if we increase the chemical concentration in the liquid, the hydrogel will shrink. And this is a reversible process, so the hydrogel can shrink and swell again. If you take now such a hydrogel and place it into a valve chamber, if the hydrogel is in the swollen state, then you can see that there are small conducting channels which permit the transfer of flow from the left to the right. And if the hydrogel swells now, then the hydrogel will hit the chamber walls, and the passage of liquid from left to right is blocked. So now we have a smart valve, which we call chemo microfluidic transistor. And the advantages of using this method is that we don't need any external control for the valve. For example, no external air pressure or something like that, no external control unit, and that we can employ intrinsic feedback mechanisms. I will point out the electronic hydraulic analogy. Like we have electronic circuits, we can also draw fluidic circuits. And there are analogies or isomorphisms between quantities. So the pressure in microfluidics corresponds to voltage in electronics. The flow rate in microfluidics corresponds to a current in electronics. And as there are electrical resistors, there are also hydrodynamic resistors. However, there's one main difference. There is no equivalent to chemical concentrations in electronics. And this main difference leads to, has an impact on the design of such systems and also on the computer-aided design methods that we develop for it. We can couple the disciplines of chemistry and fluidics to couple from the chemical domain to the fluidic domain. So to couple from concentrations to flow rates, we use our chemofluidic transistor because the size of the hydrogel depends on the concentration. And if we change the concentration, the resistance of the transistor will change, so that in the end, the flow rate that comes out of the transistor depends on the chemical concentration. And to couple back from the world of fluidics to the world of chemistry, so from flow rates to concentrations, we use a mixing junction, which has two incoming flow rates, Q1 and Q2. And there's an incoming concentration. Then there's a longer mixing channel. And at the end of the channel, there's an outgoing concentration, which depends on the flow rates of the incoming concentrations. Now that we have these two coupling mechanisms, it was very natural for us to develop a model system, a chemofluidic oscillator. The principle is shown on this schematic. We have one source which provides constant pressure and pure water. Then we have another source which provides constant flow rate and a solution of alcohol. These two solutions are mixed. And then there's a longer delay channel. And then there's our chemofluidic transistor with an outlet to a drain and also a bypass, which keeps constant flow coming to the chemofluidic transistor. And in this system, there's a closed feedback loop because the concentration that is created at the mixing junction depends on the resistance of the chemofluidic transistor. And this resistance in turn depends on the concentration at the chemofluidic transistor. The oscillation happens as follows. If we start with a high concentration at the hydrogel, this will yield a shrunken hydrogel, which means that the resistance of the chemofluidic transistor is low. This will lead to a low concentration at the mixing junction. This low concentration will then travel through the delay channel, reach the hydrogel, will make the hydrogel swell. Then the resistance of the chemofluidic transistor is high. And this in turn will lead to a high concentration at the mixing junction. And then this high concentration will travel through the delay channel, reach the hydrogel, and the cycle starts anew. Now I will show you a video of the oscillator. Here you have the constant pressure source on the top right. On the bottom left, you have the constant alcohol source. Then there's the mixing junction. And you see now the transistor blocks. Now the transistor opens. And you can also see in the delay line how the concentration changes depending on the flow rates at the mixing junction. On the top left, you can see a measurement of the flow rates. the oscillator provided stable oscillations over many hours. And what is also very nice, by changing the operational parameters of the pump, we can tune the frequency by about a factor of 5. Now that we know what hydrogel-based microfluidics is, I will explain our computer-aided design method. The idea is to use a schematic design. In this schematic, you see the oscillator. So we have components like the buffer line, the mixer, the delay line, the chemofluidic transistor, the bypass line, and also the pumps. And these components are connected by connection lines. The blue lines correspond to flow rate pressure pairs, which is the conservative quantity. And for the concentration, we use signal flow quantities. And the components are described in the hardware description language Verilog AMS. AMS stands for Analog Mixed Signal. And as a design framework, we use Cadence Virtuoso, which is usually used in electronic design automation. The advantages of using such a schematic design instead of full 3D description with partial differential equations and finite element methods are that first, we have a reduced number of degrees of freedom, which means that our simulations are very fast. And also the schematic design is very intuitive because we simply need to place the components like an electronic circuit and then connect the components, and then we can simulate the behavior. I will explain how the different components are modeled. The microfluidic channel has two effects. The first effect is that it acts as a hydrodynamic resistance. So the flow rate that goes through the channel is calculated by the pressure divided by the hydrodynamic resistance. This is realized via the analog part of Verilog AMS. And the second effect is a transport delay. A concentration that comes into the channel needs some time until it is transported to the end of the channel. And in the channel, there is a concentration distribution which is shifted along the channel due to the flow rate. And this transport delay was realized via the digital part of Verilog AMS because we need to keep book of the internal state of the concentration distribution. And this realization and also the coupling of the analog part and the digital part were the critical issues for the microfluidic channel. The mixing junction has two incoming flows of flow rates Q in 1 and Q in 2, which carry concentrations C in 1 and C in 2. Then there's the channel for diffusive mixing. And the resulting concentration at the output is simply the weighted average of the concentrations weighted by the flow rates that are coming in. Finally, our chemofluidic transistor, which has a chamber of chamber size W chamber, and the hydrogel has a diameter. And this hydrogel has a free equilibrium swelling length LEQ, which is the red curve that you can see on the graph. So for low concentrations, it is swollen. For high concentration, it is in the shrunken state. And there's a swelling rate, which is low for low concentrations and high for high concentrations. And when the concentration changes, the gel will react by a first order differential equation. So the derivative of the size of the gel is simply the swelling rate times the deviation of the current gel size from the equilibrium size times some correction factor that we learned we had to introduce. If this value L3 is bigger than the chamber size, then the transistor is blocked, of course, because the hydrogel hits the chamber walls. And if the hydrogel size is smaller than the chamber size, then the hydrodynamic resistance will depend on the difference of the chamber size and the gel size, and can be calculated by the Hagen-Poiseuille law for rectangular channels. Now we come to the simulation results. On the top left picture, you can see the measurement again, and below you see the simulation results. the agreement of simulation, experiment, and frequency and amplitude were roughly better than 80%. And what is also very nice is that we can not only use the simulation to predict behavior in the design of a system, but we can also use it to introspect our system once we have constructed our system and turn on the simulation. We can use it to access information that is very difficult to obtain experimentally. In our case, the concentrations are very difficult to measure, and we can use it in this case to access the concentration at the bypass. So in the top right image, you see the concentration at the bypass. To conclude, hydrogel-based valves facilitate microfluidic flow control by internal feedback. Schematic microfluidic modeling facilitates fast simulation and intuitive design. The methodology proved its usability in the top-down design of a chemofluidic oscillator. If you're more interested in the oscillator and the microfluidic CAD system, you can look at these two publications. The first one appeared in Advanced Materials Technologies, and the second one in IEEE TCAD. I thank you very much for your attention, and I'm open to take your questions.
Okay, thank you, Andreas, for this very interesting first talk. So I hope there are some questions in the audience.
If nobody speaks, I will not use the in the attendee manual. You said you should say hello, and then, but I will ask anyway. Just one process question to Andreas. I'm not I don't use hydrogels anyway, so I don't know them. But the very common material in microfluidics is PDMS. Mm-hmm. And then hydrogel is another one. So in terms of process, how do you make that the hydrogel is where you want it to be? Is it very difficult, or
yeah, okay. Mm-hmm. The simplest method is, of course, to fabricate the hydrogel first, and then for small systems you can place them manually. But what we are doing now is that we polymerize the hydrogel on a glass slide, and then fabricate the channels in another layer, and then we can do a flip chip technique that we basically connect the slide where the hydrogels are attached to the layer where the microfluidic channels are.
Okay, thank you. So it's a real complicated process. It's not so easy to do. And I have another question.
No, it's not. No, it's not complicated, because you just need to polymerize the hydrogels on one slide, and you need to fabricate your channel separately, and then attach these two slides. The only part that's a bit complicated is the alignment of these two slides.
Yeah. And I have just another question, but it's completely outside. You're using which operating system are you using? It seems that it's not the common one. Is it Ubuntu?
Okay. Now I'm on Linux. Yeah, Ubuntu.
Okay.
Yes.
Thank you very much.
Okay, thank you. Just because it sounds very easy from the point of view of an attendee or from a chairman to know who's talking. So if you do not raise your hand and you want to ask a question, please state who you are before stating your question, please. So I saw that was Emil, but I had to find to look for him. So we maybe have one very short question. So I saw there was no electrical equivalent of concentration. So that was one of the issues you had at the modeling level. I was wondering if that was one of the reasons why you choose a very log AMS rather than VHDL AMS, or why is there a particular reason why you choose this modeling language rather than another one?
Yeah, exactly. We need both parts. The AMS stands for analog and mixed signal, and the analog part. There's also Verilog A, which is only analog, and there's of course also just Verilog, which is only digital. And we need really both parts because to incorporate these the effects of the concentration. Yeah. So if you're not interested in concentrations, only in pressure and current, Verilog A would have been enough. But because we need concentrations, we have to use AMS.
Okay. So, okay, thank you very much, Andreas, for the nice talk. We'll skip to the second talk of this session, which is given by Laurent Latour, who got a PhD degree in microelectronics in 1999 from Montpellier University. Did a postdoc for 1 year at UCLA working on micro-machining technology for MEMS, and became an assistant professor at Montpellier University in 2001. He was promoted to a professor position in 2012 and took the head of the electrical engineering department of Polytech Montpellier School until 2018, and is now the head of the microelectronic department of the LIAM laboratory. So research interest covers low power embedded systems, signal processing, and microelectronic analog design. So Laurent, the floor is yours.
Thank you, Jérôme. Can you hear me?
Yes, very well.
Okay, that's fine. And you see my presentation also?
Yes, as well.
Okay, so I can start. So thank you for the introduction. So I'd like to thank my co-authors. John is my PhD student working with me on that project. And Simon Chamaillet is a colleague from the ecology field working with CEF, who is actually the leader of that project. So below are our institutions, labs, and those who gave money for that project. And I'd like to thank them. So what are we doing in this project? We do loggers. So loggers are data recorders, small data recorders that we usually put on collars to monitor the activity of wild animals. So ecologists have been using such instruments for some time now, mostly GPS and IMUs to monitor location and movement. But it appears that only this kind of data is not enough to identify and model animals' behavior. And we believe that bringing audio, especially into the data that is recorded, brings a lot of more information to understand what those animals are actually doing. And what you can see here has been collected on zebras. And you can analyze when they eat or when they snort, given that the snort noise is an indicator of well-being, it seems. So this is what we do in this project. And this will be the outline of my presentation. So I will start presenting some previous work very shortly. And then I will introduce the new device that we developed, which is called AudioLogger XLM, because on top of audio recording, we also bring inertial data, such as accelerations and magnetic field. So I will go through hardware architecture, then how we manage available memory, which is few actually, and then go through some firmware architecture, and then I will present results. Mostly, what we focus is the power consumption, because this is a major constraint for those systems. And then I will conclude. So what we've done previously, we developed a first generation of audio recorder. So it was audio only, based on a waterproof microphone from Knowles. And we put the analog to digital converter on board as a sigma delta modulator, which is good to avoid aliasing problems, and it's good also for the power consumption. And in that first study, we investigated the opportunity to perform onboard audio compression, and we investigated mostly ADPCM algorithm because it is simple. It does not require too much CPU to do the compression, and we studied the effect of this compression on the audio quality, depending on other parameters, mainly the audio sampling rate. And we can see how the noise floor moves depending on the parameters, and with and without this ADPCM onboard compression. So that was a contribution, and what we demonstrate, and that was nice to see this, is that doing the audio compression on board actually saves power, because doing that we have less data to store onto the mass storage, which is a SD card in our case. And we see that most of the power consumption comes from the writing operation onto the SD card. So by reducing the amount of data to write, we actually save power, and it's better even if you include the extra power you need on the CPU to perform the compression. So actually we could save about 30% of power when we compare with and without compression. And that allows us to develop audio recorder that was very low in terms of power consumption, like 6 milliwatts. It was like 1 order of magnitude better than what you could get on the market at that time. So that was the previous work. And what I present today is the second generation of these loggers that we call XLM, because in addition of audio recording, we also provide accelerations and magnetic field recording. So the hardware architecture is almost the same. We use this time a digital microphone from ST Micro, which provides directly a pulse density modulation stream at its output. So it has the sigma delta modulator integrated together with the microphone in the same package. And we use a device also from ST Micro, which is in the eCompass product range from ST. So it's basically a compass, so a magnetic field, a 3D magnetic field sensor, but it has also a 3D acceleration measurement unit to compensate for tilt. But this device provides both 3D acceleration and 3D magnetic field, and it is easily interfaced with the microcontroller by means of a SPI interface. So the new challenges that we faced with such a device is that we have very few memories, so we need to manage the way we use the memory inside of the MCU, because the more we buffer, the less we have writing events on the SD card, and the best it is for the power consumption. Also, we have to deal with asynchronous events, because each of these sensors delivers its data at its own rate, and we have no synchronization between all those events. Also, we want the data to be aligned, at least at the post-process. After we retrieve the results, we want to be able to align data between audio and inertial data. So we have to deal with this, and of course, everything we need to keep the power consumption under control very strongly. So regarding the audio data stream, we have the microphone that provides a flow of audio data. All the first buffering process is fully hardware, because that is the digital filter for sigma delta modulator. It's a peripheral inside of the MCU. It decodes the PDM stream and provides samples that are conveyed using a DMA into a first layer of RAM buffer. When that buffer is filled, we call the CPU to perform the ADPCM compression, and then we store 10 blocks of ADPCM data. And when we've done that 6 times, then we call the CPU again to store the samples into the SD card. And we considered 2 use cases. One is a lower audio sampling rate, like 8 kilohertz, that we could see as a low fee and high autonomy case, and a second case with a better audio sampling rate that we call 32 kilohertz. It's not really 32. That provides a much better audio quality at a price of a higher power consumption. So what you can see on this table is that on these 2 use cases, the writing events on the SD card have a period of about 4 seconds in the case of the low fee situation, and every second in the case of the high fee situation. And what we write on the SD card is a fully compliant WAVE ADPCM file. So it's based on the Microsoft standards. So the file can be read directly on the software like Audacity. It's a freeware that many people use in the research community. But we had to modify slightly the standard header of the WAV file to include a time code, and we do that to be able to align data with the inertial data that we collect besides audio data. So we investigated several possibilities, and we find a location in the header that we can put an extra field, which is a 4-byte field. So it's a 32-bit time code based on an hardware count. And that is used to timestamp the audio data. So regarding the other sensors, so we have accelerations and the magnetic field. So those are coming from the device, the inertial device eCompass from ST. And the buffering scheme is much simpler because we do not process the data. We just store raw sensor information into the SD card. Just every sample, so every 3D sample made of X and Y and Z is also timestamped by the same time code as we use for audio. And that's for the alignment. And you see, we have a fixed configuration of 50 Hertz output data rate for the accelerometers and 10 Hertz output data rate for the magnetometers, which leads to a write onto the SD card every 10 seconds for accelerations and every 50 seconds for the magnetometers. So when you look here at the overall RAM usage, you can see that almost 3/4 of the available RAM here, so 75%, is dedicated to sensors data buffering. And what remains here is for the rest of the firmware. And half of the total available RAM is dedicated to audio, because this is where we have the higher data rates, of course. So another issue we have to deal with this device is that writing onto the SD card takes an indeterministic time. What you see in this plot is a distribution of writing times that we obtained using a very simple test bench, where we sequentially write the same amount of data in consecutive sectors on the SD card. And what you see is that most of the time, the writing operation lasts 7 milliseconds, but in some casual cases, that seems to repeat with a pseudo-regular pattern. We have very long writing times. And that's not under our control. because that's something that is performed inside of the SD card itself. It's the controller inside of the SD card that do some housework. We don't know exactly what's inside, but we have to cope with very long writing times. So that's something I wanted to point out, because it's something that we have to deal with. And regarding the overall firmware architecture, so given that we have 3 sensors that provide data asynchronously, the IMU has its own oscillators, and when it has data available, it just sends an interrupt to the microcontroller, and then we have to collect the data, and it runs on its own oscillators. So because of that, and because of the unpredictable SD writing times, we needed the strategy where we can use the CPU resource where it's needed, when it's needed, and only that. And for that, we used a RTOS. So to be specific, it's free RTOS. And using this, we can lower the CPU frequency. So we use 4 megahertz when we consider the low fee use case. And that allows us to reduce the power consumption. And I'm not going into the detail here, but during the recording process, we have 3 tasks running in parallel. Each of these tasks is just buffering the sensor's data, audio, acceleration, and magnetic fields. When the buffers are full, there's a message that is sent to a 4th task that we call a gatekeeper, because that's the only one able to perform SD write operation. And requests are stored into a queue, so no sample is lost. And doing that, we have a CPU that is where we need it, when we need it only. And the rest of the time, we can put it into sleep mode, for instance. So that's the results that we got. So the green, so what you see on this graph is the battery discharge over time when it's recording. So it's recording always 24 hours, 7 days. So you see the green curve is our reference. So it was the first generation device where we had only audio, and we were able to sustain about 900 hours of full-time recording. So it's quite good, because putting a logger on a collar on a lion costs actually a lot. So the priority is to have as much data as we can. So 38 days was very good. And what you see with the second curve, so the one obtained with the second device, the same battery, but we also record accelerations and magnetic field. So we have, of course, a reduced autonomy, but that's still quite good, with 8 milliwatts of power consumption and up to 1 month of full-time recording. And when we consider the high-fee case of 32 kilohertz of audio data rates, then of course the autonomy is cut by more than half, but still we're close to 2 weeks of full-time recording, and it has some applications, maybe not with wild animals, but with domestic animals. We have collaboration with another research team that study horses, and they use that high fidelity configuration. Another thing, so that's what we can get from the loggers as the post-process. So we collect the data on the SD card. I didn't mention
Laurent, you are running a bit over time, so can
that's my last one.
Okay.
Okay. So the device is not communicating. We get the data from the SD card, and what you can just what I just want to show on this slide is that data is perfectly aligned, and that's what we wanted to do. And as a conclusion, I'm just saying that we have something that is now close to a product, and we already fabricated 200 of those loggers, which we provide to research teams, not all over the world, but those are French studies. This one on Rhodeals is in South Africa, and Mountain Lions is in California. So thank you, Jérôme. I will stop there.
Okay. Thank you very much, Laurent. Maybe we have time for one very short question. I have plenty, but I will keep them for the breakout room. But if you have a very short question, just ask it.
Thank you.
So no question? So I guess we can skip to the next talk. So I'll give the hand to Pascal.
Sure.
Okay, thank you, Jérôme. So as Jérôme is co-author of next papers, I will take the lead for chairing the session for 20 minutes. So the next talk will be delivered by Margot Morlin. She's online. Nice.
Yes, hi.
Margot Morlin is a PhD student in electronics at Onera, Paris, and Central Supélec with a PhD advisor that should be Jérôme, if I guess.
Yes.
The subject of her research is the electronic architecture of 4 new MEMS gyroscopes for vibrating gyroscopes, I guess.
Yes.
Okay, and the paper is called, the name of the paper is Characterization of Electrical and Mechanical Coupling in MEMS Gyroscopes with Electrical Measurements. So Margot, you can share your screen, your presentation, and during the time you are sharing your presentation, I would like to inform everybody that all the papers are available. You have a link in the small manual you have received to access the papers, and also the brochure from Nadia from Nextron. So Margot, the floor is yours.
Can you see my screen?
Yeah, perfectly.
Okay. So hi everyone. As Pascal said, I'm a first-year PhD student at Onera and GIPS in France. And Jérôme is my supervisor, along with Jean Guérard, which is an Onera researcher. So today I'm going to present to you our method for the characterization of electrical and mechanical coupling in MEMS gyroscopes with electrical measurements. This work was conducted, of course, with both of my supervisors. So first, I will do a short introduction about vibrating MEMS gyroscopes. Then I will present the mathematical modeling of our method, followed by the method itself. And finally, I will expose our results. And I'll end this presentation with the conclusion and our perspective for future work. So as an introduction, I would like to remind or learn to you what is a Coriolis vibrating gyroscope, CVG. So it's a gyroscope working as following. The vibration of a mode, called drive mode, is coupled with the vibration of a second mode, called sense mode, by Coriolis effect. Here we have an example on the right of a tuning fork, but there are some other structures more sophisticated. The main objective in MEMS gyroscope is to measure the coupling induced by Coriolis effect between 2 mechanical modes. However, there are 2 main problems, 2 couplings called mechanical coupling and electrical coupling. Mechanical coupling consists in a part of the drive mode being shifted to the sense mode by an electrode misalignment. On the other hand, electrical coupling, also called capacitive coupling or fit-through, is due to a small capacitance between the action pin and the detection pin. Both these couplings overshadow the Coriolis effect component, which is our desired output. And so here we propose a way to use Nyquist diagrams to assess the amount of these parasitic couplings. Here we have a classic representation of a Bode diagram. Here, where is the electrical coupling? Where is the mechanical coupling? We cannot detect it just at first glance. However, we will show that Nyquist diagrams offer an easy way to differentiate couplings thanks to circle fitting. So about the mathematical modeling. Here we have a mathematical model of the gyroscope with its non-idealities, and for the sake of the presentation, we neglected viscous couplings. We see that there are two coupling terms, mechanical coupling, which is here in violet, and Coriolis couplings in gray. Coriolis coupling will not be taken into account in the following follow by presentation, because for the sake of the experiment, we will not apply any rotation to our gyroscope. We are interested by the mechanical coupling. So we see that in the first equation, we want only the drive component, so XD, but we have a small amount of the sense signal XS. And in the same way, we have some XD, so some drive signal in the sense signal, which is also mechanical coupling. Sorry. These equations are translated into circles when omega, so here it's a resonant, it's a frequency, sorry. So when it's near the resonance, this equation translates to circles. For fit through, we have another model, which is right here. We can see that the output of the drive mode isn't only XD, but there is also a bit of capacitive coupling here. So we have a small amount of V in. So this is not a rotation. It's not due to misalignment in electrodes or any design errors. It is really due to a small capacitance between pins on the cell. Sorry. Yes. So our method. As said before, we know that when omega is around its resonance value, data points may be represented as a circle. Here we use the Casa-and-Coupe method for the circle fitting. So it consists in minimizing this distance, which is the distance between a data point and a circle point. And our algorithm will find the best circle answering this constraint. When we obtain the circle, we will see later how we can differentiate mechanical and electrical couplings quite easily. Here we have both Bode and Nyquist representations, and we can see that we have 5 remarkable points. They are all on the amplitude diagram of Bode representation, and the 5 are present also on the circle. So it's interesting to see that these both representations are 2 different things for the same data and the same equations. So here a simulation example to illustrate our method. We see here that on the Bode representation on the left, it is quite impossible to differentiate mechanical and electrical couplings. How we can see here, there may be some couplings, but we don't know what effect is due to which coupling, to what coupling. However, on the Nyquist diagram on the right here, we can easily detect these couplings. The fit through, for example, is seen here in the relative position of both circles. So here you have what we call the foot of the circle, and here also, and this relative distance is the electrical coupling. The mechanical coupling is the amount of it's represented by the size of the small circle. Actually, the big circle, the blue one, is the drive circle, while the small circle, the red one, is the sense circle. as written here. And the diameter of the small circle, of the sense circle, represents the proportion of mechanical coupling. There is also an angle here between the circle axis and the real axis. This angle is the phase shift provided by ZD and ZS that we saw earlier. Here we have a 45-degree angle for the phase shift. It is an arbitrary value for the sake of the simulation, but in real cases, it may be really different. So now let's talk about our experimental results. Rapidly, here is our setup that we used. So we have a lock-in amplifier, the HF2LI. And so we drive with an harmonic signal, the drive mode. The sense mode, it's let open. Both of the informations are processed in the lock-in amplifier, and then circle fitting is done on a computer thanks to a Python algorithm. So here are the wanted and desired results. We can see that first, these two cells did not have the same electronic associated. Indeed, here we see that VIG A had a 45-degree angle phase shift, around 45 degree, meaning that the cutoff frequency was close to the resonance frequency. However, the angle for VIG B was near zero. We see some capacitive coupling, especially on the sense electrodes, which is particularly problematic since we know that the capacitive coupling has the same phase as the Coriolis coupling, which is, I remind you, our desired output. On the other hand, we see on the VIG-B that capacitive coupling here is much smaller than the VIG-A1 here. In fact, the VIG-B was tuned at factory level, which explains this result. Here in this table, we can see the numeric results. We obtain mechanical and capacitive couplings thanks to a scale factor. So here they are expressed in sensor output units, which is degrees per second. This kind of diagram can also be used to do some temperature study, as shown here. We see that mechanical coupling here is temperature dependent. In fact, at 20 degrees and at 50 degrees, the size of the circles of the sense circle is different. We can also determine the temperature dependence of the angle of phase shift thanks to the axes of the circles. Here, what's interesting to see is that we can track temperature dependence of each parameter independently from the others. So that's really interesting for our future work. So to conclude about this work and about the perspectives, the Nyquist diagram is a really useful tool for qualitative insights and quantitative characterization of electrical and mechanical couplings. It can be used to determine other parameters, such as quality factor or resonance widths. And in the next months, we want to use this method to characterize matched mode gyroscopes. And we also want to investigate ways of accelerating the characterization process. Thank you for your attention, and if you have questions, don't hesitate.
Thank you, Margot, for this clear presentation. We have any question in the room? No? This is the startup of the conference. People are okay. I have a small question or comment. The idea of this paper is to, in fact, is based on the fact that the phase is a more useful parameter to discriminate between the mechanical coupling and the electrical coupling, if I have well understood. Is it right?
Actually, it's just the way. The main idea is that changing our point of view and our representation using the same data can allow us to see really different things and to determine and assess at first glance the electrical and mechanical coupling. But the data is the same if we do a Bode representation or the Nyquist representation. I'm not sure if I...
in other words, what I mean is in the Bode diagram and in the Nyquist diagram, you have exactly the same information.
Yes.
This is only the way you are representing the information.
Yes, exactly.
And maybe what you highlight in your presentation is that people are looking Bode diagram more in the amplitude point of view than the phase point of view.
Yes, yes.
And in the Nyquist diagram, both are also important, are so important.
Right. Absolutely.
So because the phase is really a discriminating parameter between mechanical and electrical coupling, while the amplitude is not so discriminative. Is it right?
Yes, I think it's right.
Okay.
I don't want to be definitive, but I agree with you.
Thank you, Mario. Okay, is there any question in the room? No? So it's time to me to give the lead back to Jérôme for the next paper. We still have 3 short talks to follow. And don't hesitate to meet Margot in breakout room number 4 in 20 minutes from now or 30 minutes from now. See you.
Okay, so we have time for, yes, we have 3 short papers now. And the first paper, the first presentation will be given by Hamad Alzabi. Hamad Alzabi obtained his Bachelor of Science and Master of Science degree in Electrical Engineering and Computer Science from Khalifa University, Abu Dhabi in 2017 and 2021, respectively. And he's currently a field engineer with Transco, a transmission and dispatch company in the UAE. And his research interests are in robotics, automation, UAV, and MEMS. So, Hamad, if you can share your screen.
I don't see Hamad in the room. So maybe we can switch if Patrick is ready.
Yes, okay.
I'm ready, yes.
Yeah,
okay,
so maybe we can start with Patrick, and if Hamad joins us, we'll have the talk at the end of the session.
I will give the regular introduction then. So now after Hamad Alzabi, now we have Patrick Poulichet. So we are skipping to the actually the 5th talk of the session. Patrick Poulichet is an associate professor at Université Gustave Eiffel and the ESICOM laboratory. Is it ESICOM?
Yes, exactly. Yes.
Okay. And his fields of research are bioimpedance, RFID, HF energy harvesting, and electronics. So thank you, Professor Poulichet.
Okay, do you see my presentation?
Yes, we see and hear you well.
Okay. So our presentation is about a wearable bioimpedance analysis for hydration monitoring in medical application. Our team, I would like to thank our team, and particularly Valentin who work on this work, and also Lionel Rousseau who proposed this work, because the objective of this work is to determine the effect of the age of some implant placed in vivo, and see the variation of the impedance of this implant. I have a problem to change the slide. Just a minute. Yes, okay. Okay, so we developed the system that you can show here. And this is the two electrode that will be placed on the body of the patient. And so we want to determine the impedance and transmit the impedance without link by RF communication to the computer and see the variation of the impedance. So from the beginning of our work, we use a classical integrated circuit, and we saw some limitations. So we want to improve. First limitations was the consumption of current of this the device, of the integrated circuits. So with our system, we can control the consumption, and it's good for wearable system. Second limitation was the bandwidth, and it's what not enough for determine with precision the behavior of biological cells, for instance. So with our system, we can measure the impedance from 10 Hz to 800K. And we have some idea, and we developed another system to extend the high bandwidth. So we determine the bioimpedance analysis, and we will show in this presentation how the effect of hydration will change the impedance measured on the body of some patients. So the principle of the determination is placed there. So outside, of course, is placed biologic cells, and we have two electrodes that communicate, that is linked to the biologic cells. And so this is where on the animal or on the patients, it's supplied with a battery, and there's a link with RF communication to the computer. And when the measurement is done, it's stored on the computer, and we can analyze later. So for measuring the impedance, we have to deliver a sine wave. We apply this sine wave on the biological cells, and this amplitude determines a current. This current is converted into a voltage, and this voltage is acquired by the microcontroller. All our work is made with Texas Instruments microcontroller placed there. And when the measurement is done, we transmit to the computer that's stored, and we can see the impedance later. To do with a good precision the measurement of the impedance, we need to calibrate. We need to adjust some parameter, because we have to understand that the impedance change a lot. For instance, it can change from 1 gigaohm to 100 ohm. For 1 gigaohm, for instance, if we apply 1 volt, that is a higher voltage, we have a current around 1 nanoampere. And with 100 ohm, with 1 volt, we have a current of 10 milliamp. So the current changes a lot. So we have to adapt the impedance to have a good precision of the voltage that we will acquire. So here we have a system that changes the impedance or manually or automatically. And one other problem is that when we measure the impedance, we have some wire, we have some integrated circuits that will change the amplitude and the phase of the impedance that we want to measure. And we don't want that the electronic using for measurement change the effect of the impedance. So we have to calibrate, like classical impedance measurement system. We have to place a known value of the impedance, acquire the voltage and the phase, and after place inside the register the value and take into consideration when we will measure the impedance. So we have calibration. So to improve the measurement, we calculate the discrete Fourier transform in order to reduce the effect of the noise, because in our case, for each value of the impedance that we want to determine, we apply one frequency, for instance, 1K, for instance, and we calculate the DFT as the modulus and as a phase. And after, when we have to determine, we calculate the impedance. And after, we replace the frequency of 1K with another frequency in the range of the frequency that we want to determine. So this is the effect of the DFT. Okay, calibration. And here on this slide, we can see the results. So first, we compare our way of measurement, our system, and with classical system that is composed with analog discovery, and we measure this this circuit, and we see the two curves with the modulus here, with the phase there, on the modulus of the impedance of our system, and with analog discovery, and we can see from range from 10 Hz to 800K, that the difference is very low, around 1%. We also measure the impedance with a classical HP measurement device, and we can see also there's no deviation. And we use this device because it's well to represent the behavior of biologic cells. So now we can measure the impedance of some patients. So we place 2 electrodes on 10 volunteers, male and female. So
my apologies, Professor Poulichet, but could you please move to the conclusion?
Okay, sorry. So electrodes are placed on the body between the shoulder and the belly, and with the 10 volunteers, we ask them for drink 250 milliliters of water, and we measure the impedance before the drinking and after the drinking, and we can see that the impedance change. It change in low frequency higher than in high frequency, because we can see the effect of the current that flow outside of the cell in the extracellular parts. So now in conclusion, I present you a wearable device that can measure the impedance with a precision less than 1%. This is our system on the right, and we work on this system that can be wearable by an animal to monitor the age of an implant on the animal. Thank you for the presentation, and now I can answer your question if you have. Thank you.
So, any questions from the audience? Please don't be shy.
Hello, Jerome.
Yes.
Sorry, this is Stuart Smith, University of Edinburgh. Hi, Patrick. That's really interesting. I wanted to check something. You talk about using the AD5933, but do you actually use this, just the DDS part of it, the AD8993?
No. At the beginning of our work, we use with the AD5953, but we replace We keep the same principle of the measurement.
Yeah.
But we replace in our circuit, we don't have AD 58 and 53. But
is this because of the needing to change the signal range on the transimpedance amplifier?
Sorry?
Is this because you need to change the sensitivity of the transimpedance amplifier?
Yes, we want to extend the frequency range. We want to control the consumption also. We want to adapt the DFT, for instance. If we need a very low consumption, we can reduce the number of points that is determined for calculate the DFT, for instance.
Okay, brilliant. Thank you.
You're welcome.
Okay, we have time for one more question. If there's no question in the audience, I have maybe one question. So you say you're reaching 2% of accuracy in impedance measurements, but I was not sure if this accuracy you define applies in terms of systematic error, random error, and what are the main contributors to the error?
I think that systematic error is can be neglected because we do a calibration.
Okay.
And to be honest, we compare the result of some classical measurement device, like HP, for instance. And when we see on the documentation, the precision of this device is around a few percent, though, so we have the same range of error.
Okay, and what is the main contributor to the error in your system? This is the main cause of error.
I think the digitizations of the ADC.
Okay.
So in this case, it's 14 bits, and so in this case, we use internal ADC of the microcontroller, but we have also another work with external ADC to increase the frequency range. And with external ADC, we can increase the frequency, high frequency to around 2 megahertz. So it's interesting in some applications. And yes, in this case, it's around 14 bits. But our work is to switch impedance to have the highest voltage applied to the ADC. Because if the resistance change, if the impedance change a lot, we have to adapt the resistance.
Okay, okay, I get it. Okay, thank you very much.
Thank you very much.
Is the presenter of the fourth talk Hamad Al-Zabi in the room? I don't think so.
Yes, I am.
Yes, you are. Okay, so we can hear you. So, can you present your paper, please?
Sure. Hello, everybody. My name is Hamad Al-Zabi. I am from United Arab Emirates, UAE. I am a student at Khalifa University. I had my bachelor and master studies from Khalifa University, which is the best university at UAE, and it has many ranking, international ranking. I want to talk about, it's my pleasure first to say that I'm presenting at this conference, DTIP conference. I am going to talk about gyroscope free UAV navigation. It was in collaboration, this paper was in collaboration with my professor, Professor Ibrahim Al-Fadl. So I'm going to start the presentation now. First, I will talk about the problem formulation, how we could get this problem, and then the research, how we did the research, and then we reached this approach, our novel contributions, the algorithm itself, how it's derived, then the main MATLAB simulation, and what we have proposed as hardware prototypes, and conclusion and analysis. I hope, inshallah, I will finish everything at time or in time. For problem formulation, the problem got formulated by having a Fourier work, which is references in 1 and 2, who is Fourier work done at Khalifa University. It was PhD student who was proposing an IMU array working with MEMS accelerometers, and the proposed work was 2D IMU array, but it was resulting in unstable angular velocity. This is I forgot to say that this gyroscope-free UAV gyroscope-free UAV navigation platform, without using a gyroscope, we could measure the angular velocity of anybody. So he was proposing that work was proposing 2D IMU array, but it was unstable. For 3D IMU array, it was consumed too much power because it was using complex signal processing Kalman filters, which results or leads to computational delays, and it consumes too much power. So by proposing this algorithm, our algorithm, which was proposed by me and Professor Ibrahim, we could implement it to UAVs in case of gyroscope failures, also to get rid of some weight, also to consume less power, to get rid of some disadvantage of the proposed Fourier work done by this reference. So this gyroscope-free UAV navigation algorithm, we could apply it to drones by putting only simple constraint or geometric constraint. By using only by using only tri-accelerometers without using any gyroscope. So by going to the approach, by the collaboration with the Professor Ibrahim Al-Fadl, we proposed an algorithm how to place the tri-accelerometers with two simple constraints. Then we could compute the angular velocity, and then the main contribution also of this paper, how we tested the feasibility of the algorithm by MATLAB simulation and hardware prototype. And the MATLAB simulation was the hardest thing, and the hardware prototype we are still developing it. But I will show you some initial prototypes. For the noble contributions, it has contributed too much in identifying or having high accuracy of angular velocity achieved without gyroscope, data fusion of IMU array, which was 4 tri-axial accelerometers. It proposed optimal 3D placement of accelerometers, which could apply to gyroscope-free UAV navigation. And then the main contribution, which is MATLAB code or MATLAB simulation, and then hardware prototypes. By going to the algorithm itself, the gyroscope-free inertial navigation algorithm, first I will show you how it goes from the first line. We, as students, professors, and doctors, we know that to identify the acceleration of a point at a body, located at a body, we have to have the origin linear acceleration, then the tangential acceleration, and the centripetal acceleration. So if we want to get rid of or reduce the signal to noise ratio of the linear acceleration measurements, we have to attach like different linear acceleration tri-accelerometers to the body. For example, if we have 4 tri-accelerometers attached to the same body, to have its exact or linear acceleration, we could have the readings of each accelerometer and add it together. So we will have the average. How we could have the average? We sum up all of them. So we have, and this one is the linear acceleration of the origin of the body. So times 4. and this one the radial vectors of the accelerometers which are attached to the body. And once you do this averaging, from this formula we get our algorithm. So from the first constraint, we have two main constraints for our algorithm. The first one is to place the tri-accelerometers so that their very center coincides with the origin of the body frame. So you place all the tri-accelerometers at a distance or at a radial vector that is such way, if you sum up all of them, it will add up to 0, which is the origin of the body. So imagine that we placed all of them and we get this first constraint. We could, so this one 0 will be, you could get rid of this one, tangential acceleration, and you could get rid of this one, centripetal acceleration. So that the total will be how you could measure the total acceleration or the linear acceleration of the body. So it will, we will come with these only terms. The linear acceleration will be 4 times the linear acceleration of the body at the origin. So if we go, we could. Okay. This is the main equation. If we could replace this omega by matrix omega, so this one is skew symmetric matrix. We could replace it by putting this matrix instead of omega itself. So put it here and here. We come up to this matrix. This one is the linear acceleration of the body. This one, the linear acceleration of the origin of the body, and this one we replace it by this one. This is a matrix, not omega itself. So
Hamad, could you please skip to the conclusion of your talk?
Okay, I will skip this one. Finally, we could have have our angular velocity, which could derived by these equations. This is the. I will show you only. This is how we propose 2 trajectories. One is waypoint trajectory. This one by MATLAB. This is flowchart. This because it's a big code, MATLAB or big file. So how is this is the location of the first trajectory? This is how we could place them, and this is the results, and this is the algorithm computations and cube gyroscope. We placed a gyroscope in the center of the simulator in MATLAB, and we tested our algorithm. We had exactly with little error, and the second approach was kinematic trajectory, and this is a video, but I could not play it here. And this is the orientation of the cube because we're injecting linear acceleration and angular.
Okay, Hamad, I'm afraid we have to leave that for the breakout room discussion.
Okay, I'm going to the conclusion now.
No. We can leave the conclusion. Oh God, we can leave the conclusion for the breakout room discussion, and now let the floor to the next speaker.
Okay, no problem.
Next presentation will be given by Ali Reza Tajadin, who is a graduate student of mechatronics engineering in Sabancı University, Istanbul, Turkey. And he has a background in computational fluid dynamics and is working on microfluidics and organ chips, in fact. So Ali Reza, the floor is yours.
Okay, thank you so much. Hello, everyone. It's an absolute pleasure to being here and presenting our research about the pH measurement of the on-chip measurement of pH using a microcantilever. So without going into much details, this is the graphical abstract of and the concepts that we have in our chip and in our design. This chip can be connected to other types of the chips, like different organ-on-chips, and particularly what we aim for is the organ-on-chips. So because it is very important when we are doing experiments in organ-on-chips to precise the parameters, and it enhances the reliability of these kind of chips. So it can measure the circulating liquid when it enters and just leaves this kind of chips. So here we have the inlet of our chip. When the liquid enters, or that circulatory medium enters our chip, it goes over a micro free flow electrophoresis, where the positive and negative ions will be separated, and they enter the top and bottom channels. So the positive goes to the upper top channel, and the negative goes to the bottom top channel. And we take our samples from the negative ions, then that there is a reason for it that we will see in this part, in the chamber part, actually. So also we have a chamber that our sample and the buffer system will react inside, and there is a micro cantilever on the top of it. The buffer system is what we have been inspired by the nature, because in our title it is biomimetic approach. So it is the exact buffer system that the cell cytoplasm just has to just maintain the intercellular pH. So when we take our sample from this negative part and we introduce to this buffer system, all have negative charge ions except the produced hydrogen, which has the positive charge. So if we apply a potential to our microcantilever, which is located on the top of our chamber, we will have we will absorb the hydrogens onto it, so it will deflect. So the deflection is just proportional to the produced hydrogens, which is related with the hydroxide ions. So what we measure is POH, so we can easily convert it to pH. So this is the general idea of our design. So having said that, we can go to the different analysis that we have done during this chip. The first and most important is to study if the particles are separated completely by microphoresis, electrophoresis. So we considered a voltage and we model it in console software. And we did it with 4 different proteins, 1 weak acid and 1 weak base. And we saw that all have been separated, as we see this green zone in the middle. So if not, we might consider increasing the voltage or increasing the channel length. And in case of increasing the voltage, we might consider other things like not introducing bubbles into the channel that might clog it. Then we just deal with the design of the microcantilever, as there is a common issue when the microcantilevers just have a low quality factor when they just operate in a liquid medium. So it's a common approach that we deal with both geometry and also the topology of the cantilevers. So we defined a specific dimension for our cantilevers according to our chamber and chip size, and we went to and we used a topology optimization based MATLAB code to just reduce the structural material by 40% and reduce the stiffness, so it has a better sensitivity and deflection. And we can see that it has almost like 36% improvement in the term of deflection when we applied this optimization. And then we just went for the detection range of the proposed geometry and dimensions for this microcantilever, which has been done again by console software and a fluid structure interaction. So we did it as per different concentrations of hydrogen ion available in the chamber, that might be available in the chamber actually. So the current design and proposed dimensions are somehow feasible and give good signals, like 1 micrometer deflection, which can be which can be read out with different approaches like piezo-resistive materials or or simpler, like by optical beam measurement. So we can say that from this graph that our proposed dimensions are just have a feasible readout for the concentration above 700 millimolarity, which can be modified according to the chip size and the design of the microcantilever. But like every other protocols, measuring protocols, there are some errors, there are some positive signs and some concerns. So in our case, we can say that our chip can act autonomously, and we can measure the pH continuously and without any functionalization of the surface. The detection range and the pH range is just matched with our purpose that we are aiming. We have just aimed for the BBB on chip, blood-brain barrier on chip. So it completely matches. So the buffer system is between 6 to 8. And also there might be some sources of errors actually, like the reaction between the hydrogen and hydroxide ion, and also the temperature increase that might happen in the electrophoresis. Also, one concern that after we separate the ions in the first part, in the electrophoresis, we need to mix them again because we have dealing with laminar flow. So these kind of micromixers are an option. And I cannot change my slide. Sorry. So finally, to summarize what we did, it's a chip that can be connected to different chips like organ chip that we designed for. It separates the ions. Then the negative part will react with our buffer system and produce hydrogen ion. And we measure the amount of hydrogen ion, which can gives us the signal for pH, for pOH, which needs to be calibrated according to the medium. But we are going to go beyond that, and we start to just design the microfabrication process flow. And we can just have some other considerations like the improvement, the pH range and detection range with just substituting or thinking or considering different buffer systems. Yeah, thank you so much for your attention. I need to thank Dr. Yapıcı and Dr. Mustafaoğlu for their kind support and help during this research. And I'm open to any question.
Okay, thank you very much, Eliraza. Does anyone from the audience have some questions? If not, I have some. Don't hesitate. Yes, you are mentioning the quality factor, and then you did some topology optimization on the microcantilever to operate in the fluid. So can you tell me more about the dimensions of the cantilever and the improvement in the quality factor you get after the topology optimization and so on?
Oh, yes.
Yes.
So the chamber is like a 2 millimeter by 2 millimeter with the height of 100, according to what we just needed for our organ and chips. So we did it with a MATLAB code optimization with a SIMP method with a factor of 3 to reduce 40% of the structure material, like polyimide in this case, to have a better flexibility. So we didn't just test it for the how much improvement for the quality factor, but for the deflection as per the conducted fluid structure analysis, we have this 36% improvement in the deflection.
But that's deflection at resonance.
No, that's the deflection with the static load.
Okay.
Static load, yes, exactly.
Okay. Okay. So I'm not very much of a fabrication guy, but I saw there were a lot of questions from the reviewers of the paper on fabrication. So maybe
yes.
Since we have 1 minute left, maybe you could give us some insight into that. So Emil, you have a question?
Sure. Okay.
Yes. Do you hear me?
Yes.
Yes.
Okay, and you maybe can see me. So I had a question. I was listening to you, and I was wondering really. So the principle of operation of your sensor is simply the separation of the flow by the cantilever, and this is enough to make sensing. Did I understand well?
Yes, exactly. We actually sense the hydrogen, the produced hydrogen in the buffers in the chamber, with the reaction with the buffer system. So it is this produced hydrogen is in relation with the introduced ions, like the hydroxide ion. So what we measure, the deflection, is just what we have as POH. So we can just easily convert it to the pH of the medium or the entering liquid.
I understood well. It's a very original principle of operation. So thank you very much.
Thank you. Thank you for your question. So yeah, we are just trying to design the fabrication process. So we are just studying about the materials that we are going to do, because we are dealing with electrophoresis, and at the same time, on the other side of the chip, we have this kind of micro cantilevers. So we need some sophisticated microfabrication with some electrodes and different consideration, that because in the electrophoresis we may introduce some bubbles that we are going to just prevent it, so it may clog our channels. So in the sense of microfabrication, it's our in future work.
Okay. Thank you very much. This concludes our first session of DTIP on system level design and signal processing. So I thank all the speakers for their presentations and for staying on time. And now I invite everyone to go to the different breakout rooms to discuss in more detail the papers with their authors. Okay, thank you. Bye-bye.
So to join the breakout room, you should find at the bottom of your window something that allows you to join a breakout room. So you click on the icon, and then you can choose your breakout room. So if you want to pay a visit to Nadia Kim, you can choose breakout room number 1. If you want to pay a visit to Andreas Voigt, breakout room number 2. If you want to pay a visit to Laura Latour, breakout room number 3, and so on, depending on which one you want to discuss with. So the bottom is an icon with a large square, white square, with 4 black square inside. Divide in groups or join a breakout room, something like that.
Is given by Mr. Alexander Goritz. Alexander Goritz studied electrical engineering, microelectronic semiconductor technology at the Technical University of Dresden. He received the diploma engineer degree in 2011. And after he joined EHP technology department and started working on the development of MEMS for millimeter wave application and their thin film wafer level encapsulation. Alexander, you have the floor to present us your paper.
Okay. So, thank you very much for your nice introduction. Welcome to my presentation. Today I want to talk about my work with the title Backend of Line Modifications of a 130 nanometer Siege BiCMOS technology for monolithic integration of thin film wafer level encapsulated deep band RF switches. So, not moving the slide? Okay, good. First, I want to say something about RF switches and their monolithic integration in order to explain corresponding challenges and subsequent modifications. Afterwards, I will show how fabricated FMM switches will initially tested, and how finalized FMM switches, including all modifications, typically work. In the end, I will summarize my work. As you already know, FMMs means microelectromechanical system for radio frequency applications. In this work, the target is the monolithic integration of a capacitive shunt switch, whereas a capacitance ratio between off and on state controls the signal flow by a shifting of the resonance frequency. So FMM switches can be used for switching networks, phase shifters, and filters. Important is the protection against environmental influences in order to keep functionality. In detailed the switch consists of high voltage electrodes, which are designed in metal 4, RF signal line in metal 5, and the suspended membrane in top metal 1. And as you can see, all parts are integrated in the upper part of the 7 metal layer backend of line. So here is in a schematic, and here is a SM image, and in total in the cross section in this schematic you see, also the HV electrodes, the RF line, and the top metal 1 membrane. So as a switch, there are 2 states, the on and the off state. In off state, no voltage is applied on the HV electrodes. The distance is maximum here between the signal line and the membrane, and the conductor capacitance is low. The signal passes the signal line with almost no loss. In on state, an applied voltage exceeded and pull-in voltage, the membrane is electrostatically attracted and the distance is minimized. So the contact capacitance is maximum. The signal is coupled out now to ground, and the switch is in isolation. Before As I already said, the switch was already initially integrated. So the conditions for my work are as followed. Number 1 metal stack is adjusted for up-bend membrane center. So this can you see here in this image, which is in recording by a white light interferometer. So the target is a high membrane center for minimum insertion loss and low membrane sides for minimum pull-in voltage. Yeah. Furthermore, the FMM sleeving is done by a wet chemical etch of the sacrificial ID silicon oxide, and together with an overflow rinse and spin rinse dryer with hot nitrogen. Finally, the preservation nitride is replaced by silicon-rich nitride in order to increase the wet edge selectivity against silicon oxide from 19 to 71. Before I start with the background of line modifications, I want to highlight that every done modification bases more or less on the following facts. The ILD silicon oxide deposition on patterned surfaces could create boundaries and sidewall silicon oxide with increased edge rate. And additionally, a 40 times higher thermal expansion coefficient of aluminum copper related to silicon oxide induces an up to 3 times higher edge rate for silicon sidewall or for sidewall silicon oxide. Finally, there is a need for encapsulation against environmental influences. So to show, I have integrated here an image, an SM image, which is prepared by FIP, the focused ion beam, and cross section, and you see here an interrupted process, wet edge process. So, and you see that the side wall, also if you have the oxide deposition, we have here the side wall deposition. The side wall deposition is already etched, and the bottom is still remaining. So, yeah, and this leads to parasitic edges, for example. And this are here in this schematic here, right? Here's again the schematic in cross section, and these are the unwanted or the parasitic etchings, the electrodes, and regarding the electrodes, regarding the membrane, and also regarding the pads. And what is here also not shown is the missing encapsulation. Yeah, the first issue I want to show is the parasitic vertical release at electrodes. Yeah, already shown here. And in a tilted SEM image, you see this here. This is, the electrodes are, or in this case, one electrode is already unedged. And in actuation, with a high actuation voltage, it can appear or occur that we have a short. There's a high risk for an electrical short due to non-insulated partly released electrodes. So to prevent from this, the solution is a silicon-rich nitride-based edge stop layer, which is located on metal 4 here in the schematic. And this heavily reduces the risk for electrical short. You see this also here in this tilted SEM image. There's no one edge. So the next issue is the vertical, is a parasitic lateral release, which mainly affects the arm length of the membrane. It's shown here, and also in the SEM image here, and enlarged image zoomed in. And there is the problem that an undefined enlarged membrane arm length reduces the spring constant and stiffness of the membrane. So the electromechanical performance of the membrane is completely changed. The solution here is a metal-based lateral edge stop between metal 4 and metal 5, which is shown here. And as the image, you can see this here. And zoomed in, see now the arm length is constant. The next issue is the vertical preservation nitride, which occurs due to the standard backend of line topography on terminal 2 grid for encapsulation. So as I said, this actually belongs to the encapsulation, but from the fabrication point, it belongs to here. So in cross section as a sketch, you see the terminal 2 grid, and this should mean a hole. And due to standard backend of line topography, we have vertical nitride. And if we open the preservation nitride in order to release the MEMS, we have remaining vertical nitride, and this blocks the MEMS release. And if we want to get rid of this, one option was we just etch more, but then in the end we have wider holes. So this was actually not possible to use for encapsulation. So the solution was for this to have a leveled preservation silicon nitride, and therefore we have additionally an additional deposited oxide, and after that it's leveled to top metal 2 at 1.5 micron, and followed by a silicon-rich nitride deposition. So after opening of the MEMS area, even the standard area, we have normal states and no vertical silicon-rich nitride. This enables MEMS release and encapsulation. A further issue is a parasitic silicon edge at pads. Whereas eliminated and partly cracked silicon-rich nitride leads to part degeneration. I try to highlight this here in this schematic, in the upper part, are the pads on top of the 2. And as the images, you can see this here. We have here an under edge of the top panel 2 part in the RF pad region, and related to the complete MEMS, including all pads, we have everywhere these delaminations, and here's already cracked. Single right hand is already cracked. So to get rid of this problem, the solution is a silicon nitride-based pad-related lateral edge stop by a second pad mask, which shrinks size. So in this case, the leveled oxide on top of top panel 2 was just patterned by a standard pad mask. Then the silicon nitride deposition followed, and after that, the second pad mask was used with a shrink size. So in this case, we could realize this silicon nitride-based pad-related lateral edge stop. So as a result, you see in this SEM images, the pads are clearly defined, and even for the MEMS area, we could use this. I'll try to highlight this here also. It's also working. Finally, there's still a lack of MEMS protection. So humidity and particles can destroy the MEMS function. In order to provide a feasible protection, the thin film wafer level encapsulation is done by a high deposition rate, silicon oxide deposition at 200 degrees C, with a target height of 4000 nanometer on top of top-metal grid. Afterwards, the pad reopening by RE and the subsequent resist removing by an etch process at 220 degrees C has to be done. So you see this right here. This is actually the final state of the fabrication of this switch. We have here the release membrane. You can see also here, and the signal line, and here part of electrode, the top-metal grid, and the oxide deposition, also the thin film wafer level encapsulation is completed here. And in this SA image you see that the holes are completely closed. So this is a cross section of this here. So after fabrication, the RF-MEMS switch is tested by a CV measurement, whereas a high-frequency impedance analyzer is used. Therefore, the actuation voltage range is from -65 to 65 at voltage step width at 5 volt. Indeed, the capacitance measurement starts at 0 volt, whereas the voltage ramp up to 65 ramps down to -65 and ramps again to 0 volt. A typical result of RF-MEMS switch with the done modification is displayed in this graph here. Here we can see a clear change of the off capacitance of 60 femtofarads at 0 volt and 240 femtofarad at 60 volt. And without any hysteresis, this measurement goes this way. So yeah, this shifts the resonance frequency from 220 gigahertz to 145 gigahertz in terms of RF performance. This enables the use for millimeter wave applications, especially in D-band. So finally, I want to summarize my talk as follows. The aluminum copper-based RF-MEMS switch parts are embedded into the backend of line ILD of the 130 nanometer Siegel by CMOS technology. The RF-MEMS switch releasing is done by a wet chemical etch of the superficial ILD silicon oxide. Appropriate etch stops are created due to locally higher etch rate, which bases on both boundaries and thermomechanically stressed silicon oxide. A thin film wafer level encapsulation using an high deposition rate silicon oxide deposition at 200 degrees C on top-metal grid is realized for protection against environmental influences. And finally, the measured capacitance and its clear change switches the signal within frequencies of D-band. So as a final conclusion, the RF-MEMS switch is successfully integrated into the backend of line of IHB 130 nanometer technology for use in D-band applications. Thank you for your attention.
Thank you, Mr. Goris, for your nice presentation. Now we have time for question. There is question from audience.
Yes, yeah, if I'm all right to do that. This is Stuart Smith again. Hi, Abdulkarim. Thanks, Alexander. It's really interesting. I wondered, was there any problems from the fab about the changes that you made to the back end of line process? Was there anything that was particularly the process engineers did not want to do?
Of course, you know, if you have a standard process, you know, we are famous for high performance transistors in BiCMOS technology, Siegel especially, and so every change is critical. So there's a weakness of my work, of course. So it's first, we can successfully integrate these switches, but up to now this is not qualified. You know, so every flow has to be qualified to offer this to the customers. So so in this case, there's at least the silicon rich nitride is as stop layer is integrated, and this is not qualified at the moment.
Okay. I thought maybe the worst would be the sidewall metal, because you're using the via process to do that, right?
The sidewall metal?
The sidewall etch stop.
Okay.
Yeah, you're using the via process. Would they allow big, long, wide vias like that?
Yes, but we are talking about design rules, I guess.
Yeah.
Yes, as far as I know, there are no problems. Of course, also we had problems with the top-level 2 grid. Therefore, we had to make exceptions. Also 1.5 micron holes related to 3 micron thick metal was not that easy, but actually some trials have shown that yeah, that's working and there's no risk for any other application or fabrication.
The last thing I was going to ask was vapor etch. Have you tried that for doing the silicon oxide release rather than wet etch?
Yes, I tried this before, but also together, let's say, and actually, as for example, the etch selectivity is even higher, and of course, also the etch rate of the silicon is much higher. But there was, I was using a water-based HF process, a vapor phase etch process. So and due to the big amount of silicon oxide which has to be etched, the process is driven and was driven. And except this, besides this, there was also this oxide. What we have is we have at least after top-level 1, there's one Theos oxide, which is standardly used, and this contains carbon, and so this vapor phase etching removes oxide, and and every carbon remains there, and so it was critical. We have small particles after release, which blocks the actuation of the membrane.
Okay, great. Thank you very much.
Okay. Thank you, Stuart. We have time for one small question. If there is no question, I have just one question. Is about the high rate deposition of silicon oxide. What kind of reactor do you use to obtain such kind of high thickness of silicon oxide?
It's actually a CVD process, but the reactor, I have no idea. It's a colleague is doing this. I'm asking for. I can tell you that it is 30 nanometer per second deposition rate, and using silane, and at the pressure of 3 to 4 torr.
It's pure CVD process.
Yes.
Okay. Any other question? If not, we will now move to the next presentation. Thank you again, Mr. Grace, for your presentation. We will move to the next presentation. The presentation will be given by Mrs. Remy Toury. She is engineering. She obtained engineering degree in microelectronics from Mines Saint-Étienne School and MS degree in nanoelectronic device from Aix-Marseille University. She is now a PhD thesis. She prepared now her PhD thesis in physics and deep plasma etching of titanium. Her research focused on micro nanoelectrochemical system and more specifically on the design, fabrication, characterization of bulk titanium microstructure with application in RF circuit and implantable pressure sensors. Mrs. Toury, you have 15 minutes to present as your paper. 7 minutes to present as your paper. Sorry.
Thank you very much for this introduction. Good morning, everyone, and welcome.
You can activate the sound is your micro. Yeah.
Actually, your microphone was active, but we heard very, very low your voice.
Yeah.
Okay. Can you hear me now?
Yeah, very good.
Perfect. Well, good morning, everyone, and welcome to my presentation. This work is the outcome of a collaboration between the Grammy Lab and the company Mystic on titanium engineering. As you can see on the screen, Our topic today is titanium isotropic and anisotropic etching for MEMS applications. The use of microelectromechanical systems, MEMS, technology in medical and biological applications has increased dramatically in the past decade. Active medical implants must be incredibly small while providing high performance and reliable protection from body fluids. Typically, an implantable medical device includes a housing comprising a titanium alloy. The medical industry has used titanium in surgical and dental equipment since the 40s. Today, it can be found in a wide array of biomedical implants, such as pacemakers, eye implants, and hearing aids. Titanium is biocompatible and possesses a unique ability to bind with bone and living tissue, making it an ideal material for many other medical instruments as well. Medical fit-through are the conducting elements of a hermetic casing that allow the internal electronics to communicate with the outside environment or other electronic components, such as electrodes. Fit-throughs designed in titanium set new standards for miniaturization and reliability of electronic components in medical implants. So first of all, I'd like to give you an overview of the deep reactive ion etching technology that allows the fabrication of these next-generation fit-throughs for implants. DRIE is an etching technology used in microfabrication that uses chemically reactive plasma to remove material deposited on wafers. Although the mechanisms underlying plasma etching are complex, I will simply present a simplified description to provide some of the main features. In the case of inductively coupled plasma reactors, like the one we use, plasma is generated under low pressure by one or more electromagnetic fields applied to a gas. Highly energetic electrons transfer energy to atoms by collisions, resulting in the formation of reactive species such as ions and radicals. Different species are present in the plasma: electrons, ions, radicals, and neutral particles. All these species are constantly interacting with each other. We can say that plasma etching can be divided into two main types of interactions. The first one is the generation of chemical species, and the second one is the interaction with the surrounding surfaces. The reactive species diffuse to the surface of the substrate where they are adsorbed. The adsorbed species then react with the surface, resulting in the formation of volatile species, volatile reaction byproducts that diffuse, removing material or layers from the substrate. The subject can be looked at under the following headings. Depending on the equipment and the process parameters, plasma etching can be compared to a so-called chemical etching due to the reaction of the chemical species present in the plasma with the surface of the substrate. The substrate is etched uniformly in all directions, which we call isotropy, giving semispherical etching profiles, which can cause problems when etching very small dimensions. And then a so-called physical etching generated by the bombardment of the surface, where species then can be etched. For example, this process can be similar to sputtering. Both ways have benefits and drawbacks according to the application. A continuous SF6O2 argon plasma process was investigated. The effects of the process gas flow rates on the geometrical features of the etched trenches, like the nickel-hard mask etch rate, the etch depth, the sideways undercut, the profile angle, and the sidewall surface roughness were studied. The experimental results obtained after the etching suggested that the tapered vias of varying profile angles can be formed by balancing the chemical-assisted isotropic etching, the passivation film by oxygen, and ion-assisted passivation etching. Lateral etching can be reduced either by adjusting the oxygen flow rate or by tuning the self-bias voltage. To investigate the influence of voltage, 2 independent studies were conducted. The first one on the RF power, i.e. the RF power source connected to the cathode that generates DC bias and attracts ions to the wafer. And the second one is pressure. Contrary to what is often observed in RIE systems, in our ICP system, DC bias increases with decrease in pressure at constant RF power. So at low RF bias powers, underpassivation is observed. So there is lateral etching, which reduces the vertical etching. As the bias increases, the etching process relies mainly on ionic sputtering of the non-volatile products. So the synergetic effect between ion bombardment and chemical etching is considerably reduced, resulting in a stabilization of the etch rate and profiles that tend towards anisotropy, with the most suitable one in D. It is also consistent to observe, as shown in the second figure, a decrease in roughness on the bottom of the etch trenches as the self-bias voltage increases. However, it should be noted that the variations are synergetic with temperature, and care should be taken in interpretation. Let me briefly summarize the main issues. The experimental results obtained suggest that trenches of varying profiles can be formed by balancing the fluorine radical-assisted isotropic etching, the oxygen passivation film, and the physical bombardment to which argon contributes strongly. An optimized etching process was obtained, and profiles with straighter sidewalls were obtained. However, trench openings were slightly enlarged. Well, this brings me to the end of my presentation. Thank you for your attention.
Thank you, Mrs. Atouri, for your presentation. Now we have time for question. There is any question from audience? If I have a small question, just the substrate that you etch, it's how do you prepare your substrate?
Well, the substrate used is bulk titanium. We use commercially available grade 1 titanium wafer, and I cut the wafer in different samples. So that's why I will just show you.
And maybe just to continue, what is the mask that you use to etch the titanium?
I use a nickel hard mask that is electrodeposited, and we use some seed layers, chromium and copper seed layers, to before putting the electrodeposited nickel hard mask.
Okay, maybe if we can, I can continue the exchange during the breakout room.
Yes, of course, sure.
Yeah. If
okay,
you have,
okay.
We have.
I will ask in the breakout room. So.
Yeah.
Okay, thank you very much.
Okay, we will move now to the next presentation. The presentation will be given by Larissa Carvalho do Arrojo. She is PhD student in electronic engineering at University of Cannes. Work on MEMS fabrication, physics and materials, and also fabrication in clean room, with the background on integrated photonic for flexible optonic networks. Larissa, you have the floor, and you have 15 minutes to present us your paper.
Thank you very much. You all see the screen?
Yeah.
Okay.
It's
So
okay.
thank you for the presentation. My name is Larissa Mirelli, and I'm going to present to you a little bit of my work on the evaluation of 3 different methods to do epitaxial PZT thin films for LSMO-based MEMS devices on buffered STO on silicon substrates. So the idea here is to evaluate PZT for the development of innovative devices such as these resonant MEMS bolometers. So the bolometers, they are thermal radiation detectors. So in this case, when we have an incident radiation here, the temperature of the sensitive material, it will increase. And we can detect this increase in temperature via the top PZT that's going to actuate, and also detect in the other side as a variation in the voltage. So the idea is that the LSMO, it's absorbent in the infrared region. So when we illuminate this sample with infrared radiation, it will induce the temperature rise of the sensitive area, as we can see here. And this structure, it has to be thermally insulated so we can have a higher sensitivity. And our suspended bridges, as we perform in the GREC laboratory, they have thermal conductance as low as 10 to the minus 7 watts per Kelvin. So it's really good according to the theoretical values that we have. So in this resonant MEMS, this change, this absorption in the infrared radiation, it will be sensed via a shift in the resonant frequency of the structure. And the output signal is then the measurement of this frequency shift as a difference in the voltage. So we have a very long fabrication process to achieve this. Here you can see all the steps that take place. And I'm going to focus, in fact, in the PZT deposition. So in order to avoid the etching of the PZT, we want to pattern this PZT by lift-off. So we have a fabrication process that's simpler to implement. And by using this, our main objective is to achieve the epitaxial PZT through a room temperature process to allow this lift-off. So we're really focusing on the 6th step of the fabrication process here. And this structure has been proposed by different groups, but not yet with oxides. That's why we're using the LSMO as the basis here. So why we want to do this epitaxially, although we know all the background, the drawbacks, in fact, of using epitaxial materials, we're going to have strain attached to this. But the fact is that when you use epitaxial oxides, such as LSMO, it has a very high sensitivity to strain. Hence, it's really suitable for resonant MEMS. And also, its carry temperature is well above room temperature. So it's really suitable for uncooled sensors. So we can use it without the necessity to work in a low temperature environment. For the PZT itself, it's a well-known material for piezoelectric actuation. But when we grow it epitaxially, we're going to have larger mechanical coupling. So we can actuate it with a lower voltage and detection with a higher sensitivity. And the composition here, the whole stack, by using the PZT and the LSMO associated, is because the literature has shown that PZT, when it's on top of conductive oxide electrodes, it exhibits better performance itself instead of platinum electrodes. That's the main topic that we see with PZT in literature. So the LSMO itself, it is really good to be used as the bottom electrode because of its type of majority charge carriers. So LSMO is a p-type conducting oxide, and the PZT, it also has a characteristic of a wide band that's also a p-type semiconductor. So we don't have here a carrier injection leading to accumulation of oxygen in the interface between PZT and LSMO, and this will enhance the fatigue properties. So in our tests, we got up to 10 to the 9 cycles with very little fatigue for the samples. So the devices, they should last long enough. And for the deposition itself, we depose LSMO by PLD process on top of a buffered STO on SE. So this is to guarantee the epitaxy. So we have 20 nanometers of STO that's deposited on top of silicon substrate by molecular beam epitaxy. After, to guarantee that we don't have any molecules that would cause problems for the epitaxy of LSMO, we grow by PLD at our laboratory 6 unit cells of STO, and we continue with the growth of LSMO films. Here you can see an image in atomic force microscopy for our deposited LSMO with a very low rugosity, as you can see, so in the order of picometers. It's a really good surface. And this is the base for our for our growth of PZT material. So for the PZT, we chose this composition because it's in the morphotropic phase boundary of the PZT. So all the piezoelectric coefficients, they are maximized. We have the best, the optimization of the material itself. And we can deposit it here by sputtering, either at room temperature, that's our main objective. But after we do a rapid thermal annealing, just to guarantee the crystallization of the material, or by high temperature, it is the 600 degrees. The other option is to do it by sol gel, which is a chemical deposition with a wet deposition, in fact. And after we also do the RTA for the crystallization. So our films, they were characterized first by X-ray diffraction. That's a method to evaluate the crystallization of the films. Here, all the peaks were showed that the PZT was C-axis oriented. So it follows the orientation of our STO and LSMO. So we have a good epitaxy for all the 3 films deposited. For the piezo force microscopy, we use it with the atomic force microscopy. It's a technique that allows the imaging through this microscope of piezoelectric or ferroelectric material domains. So first of all, we use a diamond tip here to contact the top of the PZT, and the bottom electrode is the LSMO that we deposited. So by applying an AC drive voltage here, we have a deflection of the tip that's going to be measured at the photodiode.
You are now out of time. If you can conclude.
I'll just jump to the conclusions. So we showed a good polarization for the 3 methods, mainly since here in the insert, we can see the room temperature depositions. So we have the polarizations that are comparable to literature, and the coercive field is even small, is considerably small, even if we work with a small thickness, which is really good. So we can actuate it with a very low voltage. And we also showed here that by applying only 10 volts, we can fully polarize.
I think we should not to move because we have time constraint on time. Yeah. Okay.
If you have any questions.
Yeah, maybe you can exchange and conclude with in the breakout room. We have time for small question.
Okay. Thank you.
Thank you, Arisa. There is any question? I have just one question, because if I understand, the PZT is used only to actuate the membrane or cantilever.
Yeah.
Is that to obtain a resonance?
Yeah, it's to actuate, but also to detect it. We have the full structure, so we have PZT on both sides of the suspended bridge. In one side, we actuate it, we put the whole structure in vibration, and in the other side, we measured a difference in the tension to measure, in fact, the shift in frequency.
But this means that the area, the active area, it's becomes smaller because the transparency of PZT to TRS is not. Can you explain?
In fact, here the main objective is to illuminate by the back of the sample. So the substrate here could be silicon or SOS, silicon on sapphire. So in the case where we use the silicon on sapphire, it's transparent. We can illuminate by the back, so the whole suspended structure is illuminated, in fact. So the PZT, it will not influence in the radiation incidence on the LSMO itself.
Okay, thank you, Mrs. Arisa again. We will have time to discuss in the breakout room. We will now move to the next presentation. It's a recorded video. It will be given by Mrs. Arti Gupta. Short biography. She received the Bachelor of Technology degree in Electronic and Communication Engineering in 2014 from INSEAD, India, and Master Technology in Nanoscience and Nanotechnology in 2007 in New Delhi, India again. And she is now a PhD student from Indian Institute of Technology. And the thesis, the PhD thesis is related to micro and nano-textured silicon and polymer surface for high efficiency solar cell. Okay, the presentation is already shared. Mrs. Arti, you have now the floor, and you have 7 minutes to present us your paper. Maybe Pascal.
Yes. The problem is that the sound. Do you see the movie?
Yeah.
Yes.
Okay, I will start. Just say me if you hear something.
Thank you everyone for joining us in DTIP2021. I'm Arti Gupta, a research scholar at IIT Hyderabad, who would like to present the research work done in the area of anti-reflective silicon processes. I will discuss the key outcomes from the research work done by me under the joint supervision of Professor Prempal and Dr. Chandrasekhar Sharma. The topic of my presentation is a versatile way of surface texturing of silicon 100 using KOH for silicon solar cells. Before presenting our research, I would like to spend a few minutes to introduce you with the motivation of the work. If you see the current energy scenario, then 81% of the total world energy supply is coming from the fossil fuels. To produce electricity, fossil fuels are born in presence of oxygen, which results emission of CO2 into the atmosphere, which affects the environment in many ways of the global warming and climate change. Here, to utilize the renewable energy sources will be our priority, and it's clean and green. In all the renewable energy sources, sun is an evident source of energy. The sun energy can be utilized by making solar cells as energy harvesters. However, solar photovoltaic contributes 2.7% of the total world energy supply, which is very less. However, it has a huge potential. This is because of the limited efficiency of the solar cells. And this limited efficiency of solar cell is because of the three different losses: optical loss, recombination loss, and resistance loss from the solar cell. I will be discussing about the optical loss of solar cell in detail. Optical losses consist of a light which could have generated an electron hole pair but does not because the light is reflected from the front surface or because it is not absorbed. For the most common semiconductor solar cell, the entire visible spectrum has enough energy to create electron hole pairs, and therefore all visible light would ideally be absorbed. Optical loss can be minimized easily by surface texturing. As you can see here in this graph, in case of a plain silicon surface, the reflectance of incident light from the surface of a cell is around 35%. However, by surface texturing, this reflectance is reduced from 35% to around 10%. Here, we try to fabricate the light-trapping structures by using very simple and cost-effective wet etching technique. Etching of silicon 100 in alkaline solution results in pyramids or hole bounded by triple-win plane. Such kind of a geometrical structures work as excellent light-trapping structure and may potentially help in efficiency increment of solar cells. Here, Optimization of etching concentration, etching time, and etching temperature is needed to produce a uniform and dense surface morphology, because in case of a non-dense and less uniform, surface morphology, light hitting on one place may not get any nearby structure to take the second bounce and can go back to the atmosphere. Where in case of a dense and uniform surface morphology, light will easily take the multiple internal reflection, and this will help in the increment of optical path length of the light. Here in this work, we studied the effect of etching concentration and etching time on surface texturing of silicon. Figure 1 shows the step involved in the experimental process. First, silicon samples were cleaned in Piranha bath, followed by 1% HF cleaning. Then etching was done by using different concentration of KOH. Here we varied the etching concentration from 1% to 0.1% in a step of 0.58%. At a fixed temperature of 70 degrees C, and after the etching, samples were again cleaned in the DI water and then dried using air blower, and after this, samples were used for the characterization. These are the experimental parameters. Here we varied the etching concentration from 1 to 0.5, 0.18% in a step of 0.58%, and etching time was varied from 5 to 40 minutes where we have collected the sample at every 5 minutes of interval. First, reflectance study was done using very visible spectrophotometer in integrating square mode. Integrating square mode was used to calculate the total reflectance. Figure 5 shows the reflectance spectra of 1 weight percent, 0.5 weight percent, and 0.1 weight percent KH silicon samples at different etching times. If we can see, reflectance is lower in case of a 0.5 weight percent etch samples, where by increasing the etching time, reflectance is decreased up to 10 minutes. A further increase in etching time from 10 minutes to 40 minutes results in increase in reflectance values also. The lowest reflectance of around 12% was achieved in case of a 0.58% lowest 10 minute etch samples. Figure 6 shows the standard mean and standard deviation of surface roughness values with respect to the etching time in different concentration. As can be observed here, surface roughness is highest in case of a 1% etch samples at 40 minutes of etching time. However, if you can notice, the standard deviation in surface roughness value is also much higher as this concentration. This large standard deviation in surface roughness value is attributed to the non-uniformity in the structures. However, standard deviation in SQ value is very less in case of a 0.58% KH at 10 minutes of etching time. This can be the reason for the lowest reflectance at this concentration. Again, we have done the surface morphology studies for 0.58% KH eight samples. Here we found the lowest reflectance value, as we can observe here. So the structures are more dense and uniform in case of this concentration. In conclusion, we can say reflectance decrease by decrease in the etching concentration up to 0.58%, where a further decrease in etching concentration results in increase in reflectance value. Reflectance was lowest in case of a 0.58% samples, which was around 12%. Surface roughness value increases to increase in etching concentration and also with etching time. However, the least standard deviation in surface roughness value was observed in case of a 0.58% samples, which confirms our improved surface morphology in terms of uniformity. This may be the reason for the lowest reflectance in these conditions. The novelty of this work is, in this work, we achieved the lowest reflectance in very low etching concentration, that was 0.58% only, and also etching time was also very low, which was 10 minutes only. So these conditions are very favorable for large area surface texturing for solar cell fabrication. At last, this is all about the deep study of our research. I would like to acknowledge all our funding agencies and collaborators. Thank you everyone for your support and for your kind attention. Stay healthy and stay safe.
Thank you, Mrs. Arti-Gupta, for your presentation. Now we will move to the question. There is any question from audience?
Yes, I would like to ask a question. I'm Emin Martinsik from Citroën Palaiseau. My camera is here, and I'm here. Okay, so just a question about the final goal, which is to have many reflections into the surface of the silicon. Did you consider to have you make the etching on the surface and you have more or less randomly high-lux and rugosity that is made, and did you have do you have an idea of what would happen if you try to pattern to have let's say similar reflections or similar pyramids on the silicon? So would you have a better or not better results from the reflection point of view?
Yes, sir. We can also make the regular pyramids or regular structure by patterning, but this actually this and that case also maybe reflectance will be minimized more whatever we get this value. Mm-hmm. But this method is very cost effective because in this method we do not need to include the photolithography in the patterning. So that's why that was the better option. And there are literature also where by making the regular pyramids or by making some different kind of structure by photolithography, they have done the etching. But till now, literatures I have seen the lowest value is around 10% only, whatever we are also getting with this kind of structures.
Okay, thank you very much.
Thank you, Inila. We have time for one other question. Just I have maybe one short question because you Emil said about the reference, if there is some reference process to understand exactly the efficiency of your process. But the second question, because you use only the reflectance as characterization tools, do you try to see if I understand, we cannot use only that to see if the efficiency for the application that you target is the good way?
Yes, sir. There are many other parameters that also plays the role in efficiency. So till now we have measured the reflectance and have done the optical aesthetics. We are going to the device fabrication also now.
Okay.
And we can see the effect.
Okay. Thank you again for the presentation. We will move to the last presentation, and the last presentation will be given by Mr. Nizar Ben Moussa, PhD student at the College of Tunis in Manar. He worked with C2N France and CRTUN in Tunisia. He has several scientific research axes at C2N. For example, improvement of piezoelectric materials, improvement of piezoelectric materials, zinc oxide synthesis and characterization. He's also working on the synthesis of zinc oxide nanoparticle from zinc oxide nanowires for many application in optoelectronic and antibacterial application. At CRTUN, he worked on photovoltaic based on synthesis and characterization of PBS thin films on zinc oxide nanowires with the doping of zinc oxide using aluminium. And he has extensive experience in synthesis and characterization of nanomaterials and microelectronic processing. Mr. Nizar, you have 7 minutes to present us your paper. You have now the floor.
Hello.
Hello.
You say my screen?
Yeah.
Okay, good. Thank you, Mr. for this introduction. So I am Nizar Ben Moussa, PhD student in physics at the C2N laboratory and CRTN laboratory. So today I will talk with Zadano and Al-doped zinc oxide sol-gel property. Transparent conductive oxide are gaining popularity because they can be made as N-type and P-type conductive material and suit the ever-increasing demand of current technology. Recently, indium oxide is the most popular commercial tissue material, but it's expensive, and indium security may occur in the future. In order to find suitable ETO substrate, a group of material has been studied so far. This group contains zinc oxide, aluminum doped zinc oxide. Zinc oxide film has a good electrical and optical property, low chemical compound cost, and no toxic material. However, when the zinc oxide film is doped with some impurity like aluminum, the resulting film will provide high conductivity. Therefore, this film, Azu, is the most superior substrate for ETO because it has good electrical and optical property, continuous, no toxic, abound shear material, and low cost material manufacturing cost. Shown on this figure, the photoluminescence spectra of undoped ZNO and the Azo film. On this film, a characteristic narrow emission band is observed on the UV region and broad band, converting the anterior visible region, which is attributed to the emission of near band edge and the defect level edge. It's generally believed that narrow peak on the spectrum are due to free exciton and exciton complex. The visible band observed at room temperature is due to the combination of the electron or pair traffic on the center of the defect, intrinsic and extrinsic. Within the optical band gap of the material for undoped zinc oxide, the ambient emission increasing rapidly and the ambient intensity of Azu is reduced aluminum. The peak of ambient emission shift to the short wavelength side with the increasing doping resulting on a blue shift. Deconvolute Al-PL spectra to understand the influence of Al on the optical property of zinc oxide film during the preparation. We have collected Al peak location on this type. So the first peak is predicted to be exciton or band recombination. And the second peak is the blue color, the transition between conduction bond and zinc vacancy or zinc anti-set. The third peak, this is the green emission, the origin of green emission. It's the transition from deep donor level of oxygen vacancy and interstitial zinc atom to the valence bond. The fourth peak, it's the yellow emission. The yellow emission bond is due to the interstitial oxygen and the conduction bond. The fifth peak, it's the orange-red show. Under oxygen-rich condition, the zinc sector can contain interstitial oxygen. This condition, which in theory can produce the transition on the orange-red region, transition between zinc interstitial and oxygen interstitial. And the last, all the last peak, it's the red region. It's the transition between valence bond and the interstitial oxygen energy level and the conduction between with it. So now we say the XRD spectrum of the undoped zinc oxide and azothin film deposited on ETO. The main zinc oxide peak decreased when the doping increasing from 0 to 10%. This show that IL doping led to a depuration of the crystal quality from the XRD pattern and the same image measurement. It can be said that as the IL concentration increases, the grain size decreases. Zinc oxide will be crystallized on the white sector. Each primitive in it has 4 atoms on the primitive cell. The E2 mode is related to the oscillation of one substrate, while the other is still at rest. The E2 low mode is mainly related to the oscillation of the substrate zinc, and the E2 high 2 mode is mainly related to the oscillation of substrates oxygen. We note that the identifying peak of zinc oxide decreases as a function of doping, since the structure is partial deformed by the incorporation of aluminum onto the structure. Iron and the zinc oxide material have piezoelectric properties that compound each other at low velocity. Zinc oxide has a comparatively high coupling coefficient, while iron has a low K with a really high velocity. This result shows that the grain of C-oriented thin film is possible using the Sol method and lower annealing temperature. The interest on using zinc oxide sol gel as piezoelectric material and piezoelectric device open up opportunity for high opportunity frequency and biocompatible and flexible technology on modern civilization. Resistivity measurement using 4-point probe method revealed that undoped zinc oxide about 1.9 to 1.8. It's observed that resistivity decreases when Al concentration is varied from 0 to 10%. Transparent conductor aluminum doped zinc oxide thin film also have attractive mesh attention and are widely used on thin film devices as thin film transistor, solar cell, gas sensor, piezoelectric, and biosensor. On summary, we have investigated the property of zinc oxide and azo thin film for their fourth use on piezoelectric, microelectronic, and optoelectronic. Undoped zinc oxide and azo thin film are polycrystalline with transmittance of more than 80%. It decreases when Al is doped onto the zinc oxide metals to increase the metal to oxygen ratio. The C-axis 002 orientation of the undoped zinc oxide thin film annealed at 400 degrees was successfully demonstrated. We hope that the 002 peak can disperse at the Al concentration. And thank you for your attention.
Thank you, Mr. Ben Moussa, for your presentation. Now we have time for question. There is any question from audience? I can start if I can start with a question, and I give the floor for audience after. I have just one question about because when we see the characterization X-ray diffraction of zinc oxide and zinc oxide doped zinc oxide, the addition of aluminum doping induce the degradation of the crystallography of zinc oxide. Do you have any idea how to improve? Because if you consider the photovoltaic application, you need to maintain at least the quality of the materials when you introduce the doping.
Sorry, you can repeat just.
The question is about the effect of aluminum doping on the structural properties of zinc oxide.
Okay. Okay.
The comparison between red one and blue one.
Okay. The effect of the doped structure. The structure is deuteration. We show that aluminum doping allowed to deuteration of the crystal quality.
I don't hear you. The last sentence. You can just repeat this last sentence.
aluminum doping led to a deterioration of the crystal quality.
Okay. Do you mean that because you have only 2 peaks, it means that we have more the orientation improved, but you remain already you are moving to amorphous materials also, because you suppress some peaks from the spectrum, but you, in the same time you reduce the quality of the response.
Yeah, yeah.
There is any question from audience? No? Okay, if there is no question, we can stop there, and we will, before to close the session, I will just to thank all the speakers for the presentation, and also audience for to be present for all the presentation. And don't forget to join the speakers in the breakout room to more exchange about their paper. And thank you all for.
Thank you.
Now maybe I give the floor for Pascal if you want to.
So effectively, we have now some time to reach the breakout rooms.